Okay, so we're back with calculus. So I'll remind you that we're just been starting a new subject of infinite sums, and and I said that you could possibly find an infinite sum in different ways, but we will do it in one specific way, which is very intuitive. Definition.
Also, it's hui, not a book.
Thank you. Uh, Thank you. Definition. Given a sequence an, given a sequence an, we define. Lev, is everything okay? No. Is everything the same as last week? That's what I meant to ask. Not is everything okay?
Is everything wronger?
Yes. Monotone decreasing, monotone non-increasing. We define the partial sums sequence Sn to be S of n is the sum of all the elements of the original sequence of the first n elements of the original sequence. Okay, and let's see a few examples. Example, say this original sequence is 1 over n. So the original sequence contains the element 1, then half, then third, then quarter, and so forth. This is the original sequence. What would be the partial sum sequence? So it would be 1 plus half plus third until sorry, until 1 over n. So the elements of this sequence, what are they? So the first element is the first element, no change. But what would be the second one? Yeah, it's 3 halves.
It's like a reverse.
Yeah. And what would be the next one? It would be 3 halves plus a third. How much?
10-6.
10/6. So you yeah, okay, so let's think about it. So it's 9. No, I think it's 11.
Oh yes, yeah.
11. Because that's 9/6, and that's 2/6. Yeah. So and so forth. Okay. So given one sequence, we're getting a second sequence. That's the main idea behind series. Series are actually sequences, but that instead of taking the original sequence, we make a sequence of the partial sums. And each time we add the next number. And because you're computer science guys, I will show you the Python behind it. So yeah, so A of n would return 1 of n. Okay, and definition of func n will do as that. If I ask for him to print A of n, and I'll do a for loop for p in range, I don't know, 10, and func n. This will print out, sorry. This will print out the first 10 elements of the original sequence, hopefully. This is another reason for learning swearing. Okay, it's P plus 1. Because it's 0 count. I forgot for a second. Okay. So you get 1, half, third, quarter, and whatnot. What would be the partial sum sequence? So define S of n as such. For P in range n.
Yeah.
That would be horrible.
Also correct. It would be easy.
Yes. For P in range n, sum plus שווה A of n. And now I'll print
Something.
the A is plus, right?
Mhm.
Plus S
Comma.
is plus S of n. That's a string of. Sometimes Python is more pedantic.
Change the process to commas and that's it.
Really?
The one
So-
that we're the Python.
Whatever. I did it. So A and the first.
Okay.
Okay.
You didn't return anything in it.
Okay, thank you. You're right.
See, if we did this for cursor.
Yeah. Return.
We would have
Oh.
the same problem, but recursively.
Okay, so it's still not good. To work for now. And then P plus 1. That's it. Now it works. Okay. So yay. So the first element is 1, and the first element of the partial sums is also 1. That's it. Next, the next element of the original series is half, and the partial sum is the sum of the two first, 1.5. And each time I sum it up, I show the sum. So this is the element that I sum up, and I add it to the sum. Here, for example, you see I added 0.2, and I get 2.28333. Okay? So this sequence, I really like putting them both together because we can do it. I'll do it in a second.
We can do it. Python will try.
And okay. But I don't whatever. Right. The print is
Yeah, the print is the
another
problem.
thing technical. Okay. So you see, this is, and I think this is good as well, to be honest, because it shows you at least half of what I wish to show you. AN, where does AN tends to? 0. Why? Because the size of the elements that we wish to add up, sum up, is small. It's getting smaller. It tends to 0. But what about the sum? So the question is whether it's bounded or unbounded.
Sorry.
So let's look at n squared. Do the same.
Try your best and you don't succeed.
Okay. Oh, the last one, it seems so succinct. And I don't know if it's it's because it's
Because
1
it's-
over n squared. Okay.
Yeah.
In any case, you see, this is a very, very small number, tends to 0. And the sum is 1.64483. It seems to be steady on it. Can anyone guess what this number is?
1 over e.
It's not e.
And it's not what number you
1 plus 1 over e is quite close, but it's not.
It's a little more than half.
Half of pi, that's it. So the actual answer is, I can't believe you didn't
Say it's obvious.
saw it. No, I'm waiting for him to say that's exactly what you meant. Okay. So pi was not that far off. You just need to square it and then divide by 6.
Oh,
Yes.
Why didn't I think of that?
So yeah.
Oh, it's a square because it's like doing like.
So that is one of the surprising things. Actually, it's one of the sums that I cannot prove even in calculus 2. You use Fourier analysis to prove that the sum is pi squared over 6. But it could be quite surprising.
I'm just remembering the lighting books. I totally see them.
No.
That when you have.
Okay.
Okay.
So the thing is, an usually not, it doesn't, I'll give you a theorem later on when, but usually tends to 0, whereas Sn, the sum, would go anywhere, either a finite limit or infinity, or even jump around if an could be both positive and negative at will. So definition, given a sequence an and its partial sums sequence, because in Hebrew we call it sasach, which is סדרת סכומים חלקיים. So here it's partial sum sequence, so it's psst. So n and it's I was in partial sums sequence Sn, we define the sum, the infinite sum, to be what? What would you say is the infinite sum of all of an? I wish to sum up an in perpetuity to infinity. What would be the definition of the entire sum?
Pi over 3.
No, definition, not the what would be the sum here. The sum here is infinity, but how will I define it? The what? Exactly. It's the limit of the partial sums. As you go further down the line, this tends to 0 usually, and this tends to the sum, the infinite sum by definition. That's the definition we will use. Okay. So it's the limit of Sn, exactly. Okay? So that's the definition of series, and like I said, series are actually more of sequences. Okay, just instead of taking the limit of the original sequence, I take the limit of the sum of the sequence. But it does have a few specific theorems that we learn about, but we won't have like an equivalent to the definition of a limit. We won't see epsilon here at all, almost at all. because we learned theorems about limits of sequences, and now we can use them to study series. That's the idea. For example, and what is the sum from 1 to infinity of 1? So basically, what am I asking? I'm saying 1 plus 1 plus 1 infinite times, right? What do you guess the sum will be?
-1/12.
No, that's n. That's 1 plus 2 plus 3, obviously. So no. Yes, infinity. So how do I prove that? By our definition, we say look at the partial sums. What is Sn? It's the sum of the first n elements, but all of the first n elements are 1. So what is the sum of n ones?
And
N, right? And what is its limit? Infinity. So the sum from n equals 1 to infinity of 1 is infinity. Makes sense. Agreed? Another example. What is the sum from n from 1 to infinity of -1 to the n? Let's start from 0. Sometimes we do that. That's allowed. So what do I mean here? It's 1 minus 1 plus 1 minus 1 and so forth. Agreed? Number 5 will say it's half. But by our definition, what is the partial sum sequence? So it's 1 minus 1 plus 1, blah, blah, blah. And eventually you get -1 to the n. And it's not clear if it's positive or negative, right? But it very much changes the situation. Why? S1 is simply 1. S2 is 1 minus 1, which is 0. S3 is 1 minus 1 plus 1 is also 1. So it's 1, 0, 1, 0, 1, 0, 1. Okay? And what can you say about the limit of that sequence? It doesn't have a limit. Sn does not have a limit, and therefore the series. Did I actually say the word series? I didn't write it, I think. We define this. Yeah, no. The partial sum sequence is a sequence, but the sum is called a series. We define the series. Okay, a series is actually a limit of a partial sum sequence. So, and therefore the series does not converge. Note, we say a series converge. It's not a note, it's a definition. We say a series converge if the partial sum sequence has a finite limit. Otherwise, we say the series diverge. I think the main new thing here is that we don't say tends to infinity. Usually, we usually say whether the series converge or diverge. Any questions so far?
So either if the limit is infinity or it doesn't have a limit, it diverges, and if it's finite, it converges.
Okay. Exactly. We are not really interested in series that go to infinity. We are interested in the one that has a finite limit. Okay. Example. which is more of a question, but still example. And I told you, and now I write to you, and that 1 plus 1 over 2 squared plus 1 over 3 squared plus and so forth equals pi squared over 6. I have a weird and philosophical question. Is it not weird that the sum of rational numbers is irrational and is pi squared over 6, maybe it's rational, pi squared over 6 irrational? So I won't be able to answer the second question. I don't know, to be honest. But the first question is more interesting. Is it not weird that the sum of rational numbers is an irrational number?
Yes.
So I would say it's not. Why? Look at the following. Check this out. 3 plus 1/10, sorry, plus 1/10 plus 4 over 100 plus 1 over 1,000. See where I'm getting at?
So we're getting the rationality from that's in
Yeah, we are used to, that's fine, right? So actually, every real number is a series of rational and words and like quantities. That's the whole idea of the decimal system. Every number is a sum of quantities of 1 over power of 10. So it's not that relevant. It's a bit philosophical, but I think when you think about it like that, you're less surprised when you see all these different series converge to different things. Once I wrote Wolfram wrote 1.6449340. It basically tells you 1 plus 6 over 10 plus 4 over 100 plus 4 over 1,000. It always gives you a series. That's basically it's the only way we actually, it's the main way we actually look at real numbers. The other way to look at real numbers is just by their definition. The number that when you square it, you get 2. The area of the unit circle, right? This is the way we usually look at rational numbers, or using their digits, the decimal representation. And looking at the decimal representation is exactly series, saying you need to sum up the whole thing. Any questions so far? So I gave you a few examples, and now the example and the geometric sum. So what is the sum from n equals 0 to infinity of I don't remember if I did it. I probably ruined it now, but I'll just ask you a question, then delete it. When you look at 1, tell me if I did already. 1 plus x squared. What is that?
That's we did that on Sunday.
And, but not this question I'm asking now.
Okay.
What is 1 plus x squared? When you see it, what comes to mind?
It's another phone.
What?
Is the plus n.
The topic.
A parabola, and this,
Yeah.
oops, x squared, and this. No, not at all, but what you're saying is polynomial, right? What is 1 plus q squared plus q cubed?
No, it's you mean as a rational number, it's probably approaching zero. I don't know how you call it.
No, but what do you call this thing?
Also
You-
polynomial.
I know that. You call that a polynomial, and that,
Also
would you call that a polynomial? I'm not saying if it is or not, obviously they're the same.
Oh yeah, just because you did
Just
Q
looking
instead
at
of
that,
X.
would you look at that? If I didn't show you a polynomial first, and you look at that, you would say this is a polynomial.
No, because you've used Q instead of X.
So what would you say?
I'd say that
Series,
What kind of series?
geometrics.
Yeah. Okay. I wonder if it's a cultural thing, but in Israel, students always say this is a geometrical sequence, sum of the geometrical sequence, and this is a polynomial. Has to do with the way your mind works. And in the matriculation test, I think they use Q. Let's check it. Not physical. פלוס עוון 5 יחידות מתמטיקה. Okay, so geometric sequence, סדרה הנדסית, they use Q. This is the infinite sum, which is basically Turim. I think it's important to know the Hebrew name as well. Series is Turim because it doesn't translate well. Because series you would translate usually Sidra. You see, I don't know, Dexter, it's a Sidra, but on Netflix. But here, infinite sums is series, and in Hebrew it's called Turim, and sequences are Sdarot. In any case, the infinite sum is this, and we will prove it now. But I'm just saying that sometimes we will wish to think about this as a polynomial, or to be exact, as a Taylor series, but that would be in calculus 2. And for us, we'll think of it as in the Q terms, right? As a sum of a geometric sequence. Okay, so this is what we wish to calculate. And I'll start off by saying if x equals 1, we saw the sum equals infinity. Agreed? When x equals 1, it's simply the sum of ones. If and the series diverge. If x is not 1, we can continue. What is the partial sums sequence? So it's the sum of the first n elements. What is the first element? And the next? No, x. Within that. And when do we stop? No, but
And x to the power of n.
x to the power of n minus 1, 0 count, right? Yes. So this is the partial sums sequence, and you wish to know to where does it converge, if at all? What is the limit? So how can we find the limit of such a thing, of a sum of n different things? So in general, it's quite hard and we cannot. Even like I shown you before, if you sum up 1 over n squared, you get I don't know, pi squared over 6. Obviously, it's not you cannot find it yourself, but because this is a geometrical sequence, you have a way to simplify it completely. What is the sum of these elements? Do any of you remember by chance?
Zeros.
So it's
One over
from
one.
this,
One over
it's
one
this,
minus X.
basically. Okay, that's the sum of oh, there's a delay. This basically, that's the sum of the geometrical sequence, and it is equal to 1 minus x to the n over 1 minus x.
There's a different calculation for x being bigger than 1 and x being
We'll
smaller
see
than
in a minute, but so this formula is true for every x other than 1. 1 is excluded from for obvious reason, but otherwise this is true. How do we prove it? I won't do it, but how do we prove this formula? Induction. Okay, you can do this using induction. I won't do it, I assume you believe it. But the question is, so what is the infinite sum? So the infinite sum from n equals 0 to infinity of x to the n is the limit of this of the sequence. Agreed? By definition. That's why I say the limit. I take the first n element and I take a large n. That would be the approximation of the infinite sum. And now again, I'm back to a question about sequences. What is the limit of this sequence? What?
I think we can say it exactly.
What do you mean? Why?
Because you like have this auto even it could be. No.
No, it does matter, but not on n.
Oh yeah.
What is the limit here? N goes to infinity, right? X is just a parameter. So 1 is 1, and 1 minus x is 1 minus x. The whole thing is x to the n. What is the limit of x to the power of n? Not exactly.
Minus.
Not at all.
Wait.
to x.
It depends on x.
Yeah.
Yeah.
If x is smaller than 1,
So it's
then x to the power of n tends to 0. Otherwise, the series, not exactly because of the negative numbers, it could jump, and -1, it also jumps, but otherwise the series diverge. And if x is smaller than 1, then the infinite sequence, the infinite sum, sorry, the infinite series tends to what? What is the limit? But it's not 0. 0 is just this part.
Yes, it's 1 over 1.
Not over 1. 1 over. One minus x.
yeah.
Right? X is the parameter, it doesn't change. And again, if I go back to this is exactly what is written here, except one thing. They multiply by the first element, which makes sense. If you start with some element, then all of the elements of the geometrical sequence will be multiplied by it, and so the sum will be multiplied by it as well. Here we started with 1, so it's a specific example, but it's good enough to use. And that is the infinite sum. And now I'll give you an example, nice example, I think. What is the number 0.999 indefinite? Why? So we talked about it, but here I will give you an excuse using the geometrical sum, because it's 9/10 plus 9/100 plus 9/1000 and so forth, which is 9/10 times 1 plus 1/10
Oh, yeah.
plus 1/10 squared. It's a geometrical sequence. And that's 9/10 times 1/1 minus 1/10. Right, that's the 1/1 minus x. It's 9/10 times 1/9/10. Choose one. Okay. So again, by our definition, 0.99999 is actually 1. Doesn't really matter, because you see it's a matter of definitions, and I think we talked about it enough at the start of the course. But that's just something to remember. And the main thing is to remember the geometrical sum is very important, and we use it a lot. And remember that when x is between -1 and 1, it converges, and any other case it diverges. Any questions so far?
So we're going to learn about only series where the coefficient is less than 1.
No? Why?
Because
That's just for decimal systems. We sum up numbers from for different reasons altogether, not just decimal system.
no, yeah, okay, sure. I'm just saying, like, because if everything that's bigger than 1 diverges, right? Theory, like from what I understood at
Like I said, eventually the limit of the numbers will sum up will usually be 0. Mostly due to the next theorem. Assume the series sigma from n equals 1 to infinity of an converge, then an tends to 0. Note, the sum could be any number, but the size of the numbers we add up must tend to 0. Sometimes, many times, students confuse that and thinking the sum is 0. No, the sum could be pi squared over 6. But the numbers we add up must tend to 0. First of all, it makes sense. If you wish to sum up an infinite amount of numbers, you better make sure they are small. Makes sense, but that's not the proof. The proof will be as follows. Proof. Assume the series, the infinite sum, is equal to L some real number. Okay, fine. Then, by definition, the limit of a N is L. Agreed? what can you say about the limit of Sn plus 1?
Also tends to
It's also, and that's really a theorem that we learned that is important for the question in the test that I told you to do. Okay, so what would you say about Sn plus 1 minus Sn?
tends to 0.
0, right? What is S plus 1 minus Sn? If you take the sum of the first n plus 1 numbers and you take out and you subtract, sorry, the sum of the first n numbers, what do you get?
Yeah,
And
The last an plus 1. You get only the last number. So that's an plus 1, and that tends to 0. Okay, and if an plus 1 tends to 0, then obviously an tends to 0. So if the series converges as a finite limit, it must turn to 0. An example, does the following series converge? And the series will be some infinity of
no, it shouldn't because bigger than 1.
no, because the sequence inside tends to
E.
and not 0. See, that's the way you use the theorem. Every now and again it comes out in a test. Because when you try to use the techniques that I will teach you to find out if a series converges or not, you get stuck. But you just need to notice that it's not even tending to 0, right? It's actually always bigger than 1. Okay, so it's another way to answer it, but it's confusing because it's not the first thing you think of. But I will tell you, this should be the first thing you think of. The first thing is if I can find out the limit of the elements. If it's not 0, I'm done. If it is 0, I'm just starting because there could be the sum of infinite numbers is infinity or not. And let's see that or as now or no in a few seconds. Yes, okay. We will now and for a while deal specifically with positive series, and I'll define what that is. Definition and sigma from n equal 1 to infinity of n is called a positive series if an is always larger or equal to 0. So one might say, why do you call it positive? If it could be 0, simply easier. And so saying non-negative series. So a positive series is a series where all of the elements are larger or equal to 0. And you will see later why do we start with this series. but for a while we would deal with them. Proposition given an which is greater or equal to 0, it's partial sums sequence Sn is, continue the sentence. All I know is that the sequence I wish to add up consists only of positive numbers. What does it mean for the partial sum sequence?
Yeah,
It's so first thing, and it's true, it's also bigger than 0. But I wish to say something better.
It increases.
It's increasing. It's monotonic increasing. Right? Makes sense? No, increasing is larger or equal. That's the way we
okay.
define increasing. Proof, we actually did before, s plus 1 minus Sn is a n plus 1, which is bigger or equal to proof. Okay? It makes sense. I add up positive numbers, non-negative, and so Sn is monotonic increasing. Why is it important for us to notice that? What important theorem did we learn about monotonic sequence?
Why
If
does
we learn only one theorem about monotonic sequence,
I'm just
what was
wondering,
it? And it would be on the test. Yes.
why I'm wondering why it's monotonic increasing. Why wouldn't it be monotonic decreasing?
Because the sum you add numbers. Look at the
Partial sum. Okay. Okay, yeah.
here, right? I simply add up positive numbers, so the sum is getting bigger, right?
Yeah.
And that's what I'm saying.
Okay, yeah.
So what is the theorem we learn about monotonic sequences?
Something outer limit.
Either S for positive or
Oh,
positive
it's bounded.
series, yes.
Bounded tends to 0
For
or
positive series, either Sn is bounded and therefore has a finite limit, which means the series converge, or Sn is unbounded and tends to infinity, and the series diverge. So it's all about whether there is a bound for Sn. And that's what we saw when I used the Python, when I took a converging series. When I took a converging series, then you saw, we guessed, it's not proof, but that the sum is bounded, right?
Yeah.
But when I took a diverging series, let's run it up again. It's always increasing. But the question is whether or not it's bounded.
So,
And it's not that easy to tell, because you see it's increasing, but we went on for how long? 10,000, and we still didn't pass 9.7, right? See, 9.78. And you see these numbers are quite low. So it's very confusing. It's not obvious at all whether it's bounded and converging or not. The answer is no, it's not. And it's actually, and that's, you may have seen in computer science. What is the complexity of 1 plus a half plus 1 over a third until 1 over n?
The complexity.
Yeah, running complexity, running time. No, it's log of n. So if you see, it's not n. I just did 10,000 of this and I got to 9. That's not all of n. It's log of n.
Yeah,
What's the complexity?
1 plus half plus third plus fourth. I don't remember, but I exactly, but I remember that there is such a calculation in some in algorithmics.
If that's just a single loop, so then
No, not of calculating it. If you actually no, so I didn't explain myself well. If you're trying to calculate the complexity, and say the first
loop
loop
takes
will
one.
take one operation, the other one will take half operation, the other one a
okay,
third
yeah,
of
that's
operation.
simple.
That's what I mean. I don't remember how it comes about because you can never do half an operation, but
you can just not press it.
but it appears sometimes in computer science. Okay, in any case, it's like log.
Like binary search.
And there are a few different ways to prove why it's diverged. Let's think of which ways do I wish to show you.
I mean, you could make two series and sum them together, right? Like to.
No, that's not what I mean. Example, the harmonic series sigma from n equals 1 to infinity of 1 over n. That's what we've been discussing. So it tends to infinity, it's diverge. No, sorry, divergent. But the question is how to prove it. And I'm not sure why am I asking you, because you don't know. But there are two ways, and I'm struggling to choose. Why won't I do both? First, proof. And you can tell me which one you liked best or disliked least. And first proof, Sn is the sum of the first n two elements, 1 plus half plus 1/3 until 1 over n. Agreed? What is S2n? It's the sum until I have 1 over n, then 1 over n plus 1 until 1 over 2n. Agreed so far? Now look at the difference between them. What is S2n minus Sn?
N over n plus
So it's
1.
1 over n plus 1 plus 1 over n plus 2 plus 1 over n plus n, which is 2n. Agreed?
Yeah.
Let's sandwich things up. That is at least the smallest element here, which is the last one, n times. Agreed?
Yeah.
Which is n over n plus n, which is half. I like this one because it's short and sweet, but it's more of a trick. The other one has a more interesting way about it, you will see. So, but what is the conclusion?
Mm,
3 n elements is half, so
First of all, it's like infinite halves,
Yeah.
right? Because I can sum up a lot of halves. But the easiest thing to say that if Sn had a finite limit, what does this difference supposed to tend to? 0, but it tends to half. It doesn't tend to it, it's at least half. Okay? If Sn tends to a finite limit, then S to n minus Sn tends to L minus L, which is 0. In contradiction to the fact that it's larger, always larger than half. Agreed? So what is the case left? We said it's a positive series. So Sn either is bounded and its limit is a finite number, or it's unbounded. And left you, therefore, Sn is unbounded and goes to infinity. Agreed? Second proof. Second. Proof. In the segment between n and n plus 1, the minimum, maximum, just a second, I think the minimum of the function f of x equals 1 over x is, continue the sentence, sorry.
right?
No.
No, the minimum n plus 1. Okay, 1
Okay,
n
it's
over
1 over n plus 1. Great. Let's look at a drawing, graph of that. Let's say the algebra. If x figures. Where is it? What? Oh. Something went.
f is not a function.
What did I write? If x is smaller, bigger or smaller than 1 over x. I don't remember what I wrote, but that is what I meant to write. Okay? Yeah. And in the first segment between 1 and 2, the minimum is half. Agreed? So from half in 1, then from the third in 2 and 3, then integral of the quarter between 3 and 4. Let's do a few more. From 6 between 4 and 5. From 1 over 6 between 5 and 6. Okay, I think that's enough. I'll lose the numbers. I don't care too much about them. So what what are the areas of the rectangles that I drew on the board?
Um,
What is the width of each of the rectangles? Always one, right? Because 1 and 2, 2 and 3. What is the height?
1/n+1.
Right, it's half, then a third, then a quarter, and so forth. Agreed? I wanted to take the maximum, now I can't, I think. I want to say, no, it's larger than, sorry. And I'll change that for a second. So I'll take 1 here, and I'll take, and half here, and third here. Quarter, and fifth. And I'll change my text a bit. The maximum of the function is 1/n. Okay? So the the sum of the areas of the rectangles, what is it bigger than? The curve? The integral of the curve, right? The area under the curve. So the sum of the area of the rectangles is larger than the area under the curve. And I'll show you in a second. I'm saying the integral from 1 to n of 1/x dx, we can split it to integrals between 1 and 2 plus until the integral from a-1 to n, which is smaller than. So in the first area, the maximum is 1. In the second segment, it's smaller than half. And in the last segment, it's smaller than 1/a-1. So these are the rectangles that I drew here, right? Because the area under the curve of a constant function is just the area of the rectangle. So that equals to 1 times 1 plus half times 1 plus 1/n-1 times 1, which is exactly S(a-1). So we're almost done here. We've shown instead of the series, we took rectangles whose area are the elements of the series. And when we sum out the area, it's more than the area under the curve. But the area under the curve is something we can calculate, right? We saw that Sn(1) is larger than that. But what does that equal to? So Sn/1 is more than the integral from 1 to n of 1/x dx. And who remembers how do we calculate that integral? Right, it's not within this course, it's calculus 2, but it's high school, right? Calculation of areas. It's log, exactly. It's the log of n from 1 to n, which is log of n minus log of 1, which is log of n. And what happens to log of n when n tends to infinity? It's 10 to infinity, and s minus 1 is larger, even larger than that. But it tends to infinity quite slowly. The log of like 1,000,000 is, I don't know, it's a bit more than 6, right? And in the base of 10, it's 6, so it's a bit more, but it's very slow. Yes,
Can you zoom out a bit?
yes. So which proof do you like best? See,
That was done in 2 lines.
but it's shorter, I agree, but it teaches you nothing because you need to think about the trick. If I hadn't told you do s of 2n minus sn, you wouldn't get to it. But here, you wouldn't get to it either. But it makes, but it feels like you could. Whatever, I like it. That's what matters most.
Yeah. I mean, looking at it now, it's pretty obvious, but.
Yes,
Uh,
yes, that's obvious. Right? Yes,
what were you trying to prove in?
The first and second line of this proof
yes.
is
Jeez.
no, it's saying that is smaller than or that is equal to. Because on the right side,
Ah,
it's
you're right.
smaller than on the left side. Either.
Smaller than, I think it needs to be even bigger than. Bigger than. No, smaller than, sorry, smaller than is true, and smaller than. So the first part is instead of taking all of the area, I slice it up to n different areas between 1 and 2, 2 and 3 and whatnot. And then what's written here is exactly what you see here in the picture. The area under the curve is smaller than the area of the bounding rectangle, which is simply the integral of 1 of the height. And the area of this rectangle is the integral of half its height. Okay? And so that's what's going on here. And it's allowed us to prove then that's 1 plus half plus a third is at least log of n. If you do it with the rectangles which are bounded under the curve, you get half plus third plus fourth, which is just one distance away from the other sum, and it's smaller than log n. So you get it's O of log n. You will do it sometime in computer science.
I read for 5 minutes.
Because I don't remember, I wish
This
to
will be on the
find
test.
ChatGPT everything.
Just
Can you give me an example
Which is the test word?
of a program? Like you mean checkers? Of,
If that's an option.
of a program with complexity of 1 plus 1/2 plus 1/3, so forth.
It's binary search, no? Oh, no, wait, 1/3.
I know that, but program with it. That's not what I asked at all. Here's a Python example with explicitly sum the harmonic series, but that's not what I asked. I think that might be what I asked, harmonic loop, while I could tell me J, like this.
I think
and
there's a value there,
it's
but
just
yes.
increasing every time. Maybe it's
J plus 1. I don't follow, I think I understand the idea, but I don't follow the code. One half of the time. Yeah, maybe if I find the. Like, if I run on all numbers and then I run on half the numbers, even yes, odd
Binary
not,
search.
and then no, but then a third. Binary search are powers of two.
Yes.
Yeah. So then I do jumps of three. I think I remember when they ask you to look for increasing sequences in different sizes. I think it's something like that. So you skip in two,
find all
skip in
increasing-
three, and three. I'm not sure. I remember there's something like that. Apparently this seems legit. Here, yeah. Insane. While J is smaller than N over I. So I divide first I run through the whole course and then I run through half of it, then a third of it, then a fourth of it. So it didn't give me a very good reason as to why to do it. In any case, it comes up in computer science. I don't remember exactly when, but it's something like that. When you do skips,
I think it's find the
skips of
biggest.
2 steps, of 3 steps, and 4
Yeah,
steps.
find the biggest increase in subsequence, maybe.
Yeah, something like that, exactly, something like that. And then it's the original sample plus half the sample plus third the sample, so it's n log n eventually. So you will see it as well. And any questions thus far? Okay, so again, the harmonic series is quite important, not as much as the geometric sequence series, but you need them both. And the test is most of the grade.
No, I thought you were talking about the midterms.
No, the test itself. Yes, I don't know.
What do you mean you don't?
I don't care. You should relate. It's some kind of number between 0 and 20
I'll tell you
usually.
when.
Yes,
Last semester,
yes,
doing discrete math,
yes,
I got 60 on the test.
yes,
And because the test was 90% of the grade,
yes.
I got less than 60 in the course.
No, so okay, for that I can tell you. The midterms will never fail. If you pass the final test, you pass the course.
Okay, that's not why he failed, but do the homeworks.
No, it failed because it doesn't understand the material. But we're talking about how technically they failed him. Yes. Question is, did the lecturer fail you or did you fail others?
I
Yeah.
failed myself.
Yes. But that has nothing to do with it, right? Okay. No, but yeah, the quiz is a shield again. It will not fail you. Just you can fail you. Okay.
From number 3. So,
Um, I heard you, Anakin.
what do you think that's that?
Example.
I think
We wish an example.
Do we need an example?
Yeah, the harmonic already is redundant, and I'll do another redundant example. Why? Because we will later prove about the general harmonic series, a theorem about the general harmonic series, that the sum of 1 over n to the power of p is converging if and only if p is larger than 1. So it covers the harmonic where p is actually 1. It will cover the next example, 1 over 2n squared. But nevertheless, I think it's a good way to understand the material, the first few examples, so I will do it anyway. And it's a good segue into the next
To this one.
tools. Okay. So example, and does the following series converge. And the series is sum from n equals 1 to infinity of 1 over n squared. And now I wish to note we will prove that the general harmonic series sum from n equals 1 to infinity of 1 over n to the p converge if capital C, it's the same sentence, if and only if p is larger than 1. Okay, so remember it. We'll prove it, but it will take me some time to get to it. We're going to learn 5 tests of convergence test of the positive series. It will be first need to translate into English. First comparison test, limit comparison test, the ratio test, the root test, and the how do you call that in English? Condensation test. Ibui. It's Ibui, like condensation of fumes of water to.
Yeah, I will look
In
it up.
maths.
Yeah.
I thought you were doing like a Roman.
So the reason I do that is because these two are two comparison tests. Usually you do one or the other. Ratio or root goes one or the other because they are both comparison to the geometric sequence series. And the last one is different and far away, is the condensation test, which main purpose, to be honest, is this question right here. It's instead of an integral test. When you learn integrals before series, like in engineering, you don't learn the condensation test, you learn the integral test. Okay, so
We do this 5 tests to understand if it converge or.
yeah. The purpose is to decide whether a series converge or not. And we will do now on next lesson, we'll do the 5 tests. Yes,
Just one more time. A series converging means that the sum of all things
it's
doesn't-
finite limit.
It doesn't equal infinity.
It does equal a finite limit. I don't like when you say it doesn't equal infinity, because it could be like the -1 to the power of n. It could jump around, right? So it converges if the infinite sum is a finite number. That's all. Okay, everything else is divergent. In the case of positive series, you are correct, because positive series either bounded and go to a finite number or unbounded and equal infinity. But in general, convergent, it has some number. The infinite sum equals to a number.
Just think I'm a bit unclear on. Series converges the same way that a sequence.
No, it doesn't.
It doesn't.
That's what I mentioned it specifically. A series, well, it does and it does not. It depends really on language. I'm not even sure in English. In Hebrew, it's quite confusing because יש מתכנס ומתכנס במובן הרחב. I'm not sure if in English it's the same. But in any case, in sequence, I hardly use the term converges because it's confusing. I use it in series, right? So if the partial sum sequence does not have a finite limit, the series does not converge. If the partial sum limit tends to infinity or negative infinity, the series diverge. I said converge before, diverge. The only case when you would say converge, that if the Sn, the partial sum sequence, tends to a finite limit. That you have some number, you can say the infinite sum equals 3. That's converging. If it equals infinity, it does not converge. Yes?
I think so.
Is this the condensation test?
And no, it's also the root test.
Ah, wait, you also mentioned that one?
Yes. I said a ratio test, root test, condensation.
Alternating series, as you also mentioned.
One is ChatGPT.
Okay. Taylor. It's weird because I'm looking at notes from a course in English, but
Maybe they took the integral test. That's what I'm saying. It's either the condensation or the integral.
no, yeah, I'm saying it's weird because series don't appear in calculus 1, appears in calculus 2.
It's more like engineering.
Mm.
That's what happens in engineering. Then I teach the integral test. Because Weierstrass M test, it's not true at all. He's wrong.
If you Google that, well, I mean,
That's Hannah Boyd.
no, Google screw off.
Let's make. And that's the English.
In English, it doesn't exist. We don't.
List of tests, ratio test, root test, integral test, it's the integral test, direct comparison, limit comparison, Cauchy, Abel, absolute.
No, Cauchy condensation test, is it not that?
Where?
Cauchy condensation
Ah, again,
test.
condensation. Oh, it's Cauchy. I didn't know. Yeah, the condensation. Even the same thing. Yes, that's it. Okay. Not to be confused with Cauchy's convergent test. Yes, it's a different word. Okay.
Can I just say, like, not to be confused?
Yes. Not to be confused, don't read the following. It will help you not getting confused. Okay. Yes, so it is a thing, yes. Okay. That was just a quick making sure that I'm not just מחרטט בביטחון, I'm not sure if
That it translates,
if it
yes.
translates. Okay.
Professional bullshitter.
So yes. So the point is, the point of the example is that actually calculating the sum of 1 over n squared is quite hard. But a very close series is actually quite easy to calculate. Surprising, but true. So what is the so-called close example? So there are a few. I would choose from n equals 2 to infinity of 1 over n squared minus n. You can see why I did not start with 1, because then I would divide by 0. But you can guess, and maybe I'll write it in a formal theorem next time, that a finite amount of numbers does not change whether or not the series converge. It does change the sum, because if I streaking an element out, it would be streaking from the infinite sum, but it won't change whether it converges or not. So we start with 2. And what is the connection between this series and that series?
Between this one and
I mean comparison. Which is bigger? This or this? The smaller one is bigger. That's not the lower one is bigger. And the thing is that if the lower one converge, then it's the bigger one, then obviously the first one converge. What I just told you is called the comparison test. And that would be the first test that we learned. So now I just wish to show you that this is easy to compute. Okay? Intuitively, It's not intuitive to write intuitive this way. Intuitively, if the larger series converge, so is the smaller, we will learn such a theorem next time. But now I wish to calculate this. So first notice the following fact. What is 1 over n squared minus n? So it equals to 1 over n minus n minus 1, which is easily seen to be 1 over n minus 1 minus 1 over n. And why does that help us so? Because Sn is 1 over 1 squared minus 1 plus 1 over 2 squared minus 2 plus blah 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 1 over n squared minus n.
First thing.
So that
From second.
what?
Yeah,
Oh, all right. Sorry. Yes. So start with 2 and do Sn minus 1 to finish with n, which is 1 over 2 times 1 plus 1 over 3 times 2 plus blah blah 1 over n times n minus 1, which equals to
we had this in number.
would be 1 minus half plus a half
So-
minus third.
I did this last night. I'm not even
He's
joking.
taking it up a notch.
No,
Not only did were I about to say that, I actually was about to say last night I was ready with.
no, I approve.
Yeah, it's in
Wait,
our
can you scroll
homework,
up just a switch?
the telescopic sum.
But on series,
No, in,
We had to calculate the limit. Of
yeah, basically.
I see, without saying series, yeah. And there was a hint to do that?
Yes,
Okay.
Yeah, the word.
Yeah,
So what is minus half plus half?
It's 0, 0, 0, 0, and it's
Yeah.
1 minus.
So it's 1 minus 1 over n, which turns to 1. And therefore, the limit, the series is actually 1, converges to 1. And the other one is even smaller than that. But when we did it using Python, it was 1.6 because of the first element. This is the other one with the first element stricken, right? So the other one should be less than 2, which is actually true. Okay, so that's enough for today. See you on the other side. See you on Thursday.
see you. Sunday now. Oh,
Tuesday. Ah, what? Keep forgetting. This is the second day of Sunday. Sorry.
Second day of us, yes.
Yes. In the week.
Ah,
Have you not seen the colliding?
what?